Welcome to SanfordFlipMath. This is PreCalculus, working through the Demana Waits Foley Kennedy book. We are in the process of wrapping up the third chapter about exponents and log functions, and we are working through the section that's about financial formulas. We previously worked through the compound interest, exponential growth stuff, and getting a little more focused, a little more excited about this by looking at annuities this time. So what we've already done is when we've put in an account, some kind of an account, maybe a single payment, and then let it build up some interest. Well, that's not what we're doing today. What we're talking about now is the idea of if we take a multiple payment situation, a regular payment, so monthly payments, weekly payments, bi-weekly payments, annually, same, whatever. And then the problem is that we have more than one. And just to take a minute or two to try and set the framework together, if we made one payment, and let's say we were talking about a 4-year, maybe a 4-year loan or a 4-year, let's say a 4-year savings. Okay, we put a payment in, a deposit in the bank, let's say $100, and then it's going to sit there for 4 years. We're going to save up money for 4 years. So it's going to sit there for 48 months and earn interest. Okay, and then what we do is we put in a second payment of $100, and we're going to put it in on the second month. It's not going to sit there for 4 years. It's going to sit there for 47 months. And it only earns interest for 47 months. And so that would be like doing a separate problem with our compound interest formula. The third month, we put in another $100. It's going to sit there for 46 months before we get a total. And that would be yet another calculation. Okay, and the fourth month is only going to sit there for, okay, so you see the pattern here. And honestly, and I know this is going to shock you, I really don't want to do 48 calculations and then add them up, because the first $100 sits there for a different amount of time than the 47th amount of money plus the, so that's $100 plus interest plus $100 plus a different amount of interest, etc. Okay, so what we do is we have different formulas that take this into account. We are not going to go through the derivation of those formulas. I've seen it, I've done it, it's just not fun seeing where it comes from, and it's just not that exciting. So what we're going to do is just say, here's the formula, and this is how to use it, because that's a handful enough. Okay, okay, so to recap the flow chart at this point, the idea is you have to first decide how many payments you're making. If you make a single payment, again, it's compound interest. We've already done that. If you make more than one, and these formulas only work when they're regular payments. So again, on a fixed interval, monthly, annually, something like that, okay? Or anywhere in between, but it's got to be on a regular basis, weekly, monthly, bi-weekly, whatever. Okay, then you have to make a decision, when is the big money? Okay, the situation we were just talking about is considered a future value situation, because you start with zero money and it grows to the big money, however much you're saving up. Okay, so this is called a future value. The big money is in the future. Okay, if the money starts out big, I have an account with $1 million in it, and then I start making withdrawals down to $0. This is called a present value problem, because the big money is in the present. Okay, so this would be like, I have a chunk of money sitting in the bank that Grandpa left me when he passed, and now I'm going to get to take out, $100 a month just as some pocket money over the next 20 years or 5 years or whatever. Okay, so the big money happens at the beginning. Okay, one other situation that has big money up front that people don't think about this way is a loan. So like if I borrow money to buy my fancy new Mustang, and I borrow, let's say 20 grand, it's used, and then I make payments, when I pay it off, it becomes a $0 debt, okay? So it's kind of like the bank has deposited money in me. So loans are also present value, okay? So that's going to be something that we're going to have to deal with, okay? All right, having said that, here are the formulas, okay? This is, again, the flow chart, the side of the flow chart that we were just talking about. And then, so here's future value. This is its formula. Present value has its own formula. Okay, so again, this is big money. Okay, I guess it's right here. Never mind. Big money at the beginning, down to nothing. Future value means the big money is in the future. We start with none and we build it up. Okay. Now, there are some different letters in this formula, and you need to be a little careful about them. Okay. I is the interest per payment period. Okay. What that means is if I'm making monthly payments, then what I have to do is take the interest rate they give me, which might be 3%, so 0.03, and divide it by, if it's monthly, 12. Okay, so this is the interest per month will be the answer from this division. If I'm making weekly payments, it'd be divided by 52. If I'm making bi-weekly, it'd be divided by 26, that kind of thing. Okay, so interest per payment period. The interest normally is an annual number. Okay, this would be per year. And then if we divide it by 12, it now makes it per month. Okay. The other thing, well, one of the other things that is new to this formula is N. N is the number of payments. So K is the number per year, T being the number of years. So when I multiply them, I get the number of payments. So that's the total number of payments. So if I'm paying for 4 years monthly, then this is going to be 12 times 4 is 48. That's what N is. Okay. This is getting a little messy. Then the other two quantities in this in these formulas. Let's just make some room. One of them is R. R is that, now you know that if you can rewind to see all of that stuff I just erased. Don't feel like you're stuck with me going through this timeline. Okay, R is the regular payment. So in other words, if I'm making a monthly payment, R is that monthly payment. If I'm making a weekly payment, R is that weekly payment. Okay. And then these numbers are whatever the total money is that we're talking about. It's the big money that we're talking about. So in other words, if I'm in a future value problem, I'm saving up. And as I make all of these deposits into my bank account, this is that big money that we were talking about. That's how much I saved up. If we're talking about present value, then this is the big money we start with. This is, I have the $20,000 that my parents saved up for me, when I'm going to go off to college, and now it's in a bank account, and now I'm going to start taking money out. Well, that's that big money, that 20,000, whatever it is. Okay. All right. So that gives you the framework. Let's do some stuff. Okay. That's 10 minutes of explanation almost. Let's do some problems. I'm going to shoot for 2 or 3. We'll see how it goes. Okay. All right. Saving up $50 per week in an account, earning 3% interest. How much will be saved at the end of 4 years? Okay. So the first question is this more than one payment? Okay. Well, $50 per week. This is more than one payment. So this is not a regular compound interest problem. This is an annuity problem. This is a future value or present value. Okay. How much will be saved at the end of 4 years? So the next question is, where is the big money? Well, we start out with no money, and then we're going to save up money by putting money in the bank. So the big money is in the future. Okay, so this is a future value problem. Okay, so we're going to follow this formula. $50 per week. Well, that's the regular payment. That's R. Okay. In an account earning 3% interest. Well, this is not I all by itself, but that's part of I. Per week divided by 52. So remember, I is R over K. Now, don't confuse the R's. This is little r, the interest rate, like we were working with before. Big R is the regular payment. Okay. How much will be saved at the end of 4 years? Okay, that's going to be how much will be saved. That's going to be the FV. And then 4 years, well, N is K times T. We're making weekly payments for 4 years. So this is going to be 208 for N. All right, well, isn't that exciting? We have to have formulas to figure out the variables for our formulas. Well, that's welcome to PreCalculus. All right, so here we go. Future value is R times 1 plus I let me scooch that up so you can see where I got that from, to the N. So that's 208 minus 1. Grouping symbols are going to be incredibly important for this. Over I. And I will tell you that you really don't need the big parentheses. Instead, what I would do now, if you're working on the new system for the TI-84, then you are in luck because this can be a jacked up mess. I would do this, and although the formulas are typically written the other way, I would group them more like that. Okay? All right, so let us do some typing together. You will definitely want to write this down separately. I have written it down separately, so you won't see it on the screen, the formula on the screen while I'm typing, because I have to have the calculator up. All right, so here we go. 50. Now I'm going to open up the numerator, and I'm going to now open up the parentheses inside the numerator. I don't need a separate set of parentheses for just this little division, so I'm not going to put any. 208. I am working the new system, but I'm trying to type it in a little more like the old system. I guess I could have shut off the math view, but now close parentheses for the numerator, divided by open parentheses for the denominator, so you can hold together the 0.03 over 52. Now, I doubled the 5. I know some people would prefer to do some of these little calculations separately, and you can do that. My only concern is, and you probably already know, rounding. You cannot round intermediate steps, and when you're talking about raising something to the 208th power, that's a huge deal. So just a quick little aside here. If I had just this part, okay, because some people would want to type that in separately. If I type this in as 1.0, I'm not making any interest anymore. I cannot do that. I need to have that whole chunk there. I need, I mean, lots of decimal places. You have to have it. Okay. All right, so all said and done, this was $11,046, and we'll call it 35 cents since it was 346. Okay, now one other little aside here. Okay, I want to pop back over to the calculator for just a second. Now remember, we made 208 payments of $50. So how much did we really put in the bank? Well, we really put in the bank $10,400. $10,400. This is what we really put in the bank. We put in $50 a month, a week, times 208 weeks, and this is how much money we put in the bank. I want to emphasize the fact that suddenly the bank is your friend. You made over $1,000 just by having your money sit there. This is not money that you put in. That interest, this is the interest that that account made over those years that you've been putting money in the bank. Okay, so this is your friend. Interest is your friend when you're putting money in and you're earning the interest. Okay, it won't be the case the other way around. All right. Well, I think what's going to happen now is we're going to do one more example and then we'll be done. Okay, so I want to do one that's kind of backwards. It says we want to borrow $25,000 for 4 years. So we're borrowing money now. We're going to take 4 years to pay it back, and the bank charges us 6% interest. Now you need to know that banks always charge more for interest when you're paying money back than they pay out in interest. You know, because banks, as you might be unaware, banks are in the business to make money. So they're not going to give you more money than they bring in. Okay, so we want to borrow $2,500 for 4 years. It's a 6% loan. We want a monthly payment. So we're going to calculate our monthly payment. This is probably the most common use for these formulas, and that's figuring out how much do I have to pay every month. I want to buy a car. How much am I going to have to pay every month? I have to, want to buy a house. These formulas are used for calculating loan amounts all the time. Okay? Because the big money is at the beginning, because you're borrowing money, the amount that goes on the bank ledger is 25 grand, or 2,500, sorry, I keep saying 25 grand, 2,500 right out of the chute. Okay, so I charge something on my charge card for $2,500. I want it to be paid back in 4 years. The charge card is giving me a sweet deal of 6%. Charge cards are usually in the 15 to 25% range, which is a whole lot more. All right, so we're going to borrow, since the big money is at the future, or I'm sorry, the big money is in the present, it is in the now, it is the PV, and that number is the PV, the present value. Okay. N is going to be K times T. Well, we're making monthly payments for 4 years. I is 6% interest, so 0.06 divided by the number of payments per year, because this is the percent is per year. So I need the per year number here. So this is going to be over 12 because it's monthly. And now this calculation is actually pretty easy to do. So if you want to go ahead and just do that one, it comes out nice. We don't have to worry about crazy decimals. Okay. I think I'm going to go ahead and write it in the formula like this just because it doesn't always work that way, and I want you to see how it looks. Okay. All right. So the question then is, what's the regular payment? That's what I want to know. So present value equals, I want to know R. Now notice this formula is slightly different. It's really similar, but it's different. So I is 0.06 over 12 to the, please note the negative sign in the exponent this time. And I know the print is small on the screen, especially if you're watching this on your phone. Okay. Okay, so again, there's a negative sign in that exponent. That's a big deal. If you miss it, it's going to get jacked up. Your calculator is going to scream at you maybe, and you're not going to be happy. Okay, Mr. Sanford, my calculator is broken. Yep, it sure is. Throw it away. No, I'm just kidding. All right, one other quick note. I will probably not type things in with the giant parentheses. What I will do instead is really put parentheses around this part and this part. Now, I'm going to go ahead and type it in with the new system just so you see how it looks with the fraction-y stuff. Okay, and I just noticed that I didn't actually put the I in. I think that's funny. Somebody's out there yelling at me, Mr. Sanford, you forgot to put the numbers in for I. Yes, I did. Sorry. Okay, so now one other thing here is I'm actually going to type in this whole thing on the right side, So this is all going to be a number, and then I'll have 2,500 equals R times whatever that number is. Okay, so I'm going to leave this screen. We're going to go to the calculator and type this in. Okay, we're going to type the right side in. Okay, here we go. Okay, so let me clear. Don't want to be distracted by all that stuff. All right, so here we go, right side. I'm going to type this in like a fraction. Okay, so I did alpha y equals, and this is on the new system. So my numerator is going to be 1 minus parentheses 1 plus 0.06 over 12, close parentheses, raised to the negative 48. Going in the denominator now, this is going to just be 0.06 over 12. This is a little nicer because it looks a little bit more like a fraction. And all of this is 42.5803 whatever. Now, a quick little note to self. I'm going to pop back over to the other screen so we can remember what we just did. This is the 42.503 bunch of stuff. So now what I'm going to do is divide both sides by that number. Okay, so R is going to equal, okay, so this is 2,500 divided by that answer. So 2,500 divided by that answer equals 58.71. $58.71 per month. Okay, so if I pay $58.71 per month, for 48 months. Now, I'm just a little curious to see how much money this is. 58.71 times 48. This is to pay back a $2,500 loan. 2818.08. Okay, cool. So quick little backtrack here. We borrowed 2,500 bucks. We spent 4 years paying it back, and we actually paid an extra $2,818. We paid an extra $318. So that $318 is money that the bank made. Okay, so just a quick clarification on a couple of things here. The question asked for the monthly payment. That's this. Done. Side question, how much money did we really pay? Well, we really paid 48 payments of $58.71, which is 2,800 bucks. When we borrowed 2,500 bucks. Okay, moral of the story, avoid borrowing, because you're going to pay a lot more money than what you really should be paying. If you're trying to buy something for $2,500, you're going to pay an extra 300 bucks. Maybe 300 bucks doesn't sound like a lot to you, but when you start talking, if this would have been $25,000, you would have paid an extra $3,000. It's $250,000, you would have paid an extra, so the money goes up. So anyway, I'm going to leave it at that. This is SanfordFlipMath, and we are out. Bye.